course, I would like to start by thanking the organizers for the invitation to this very special meeting. It's a pity, I think, that we can't meet in person today in Warsaw. But on the other hand, I think it's also great that we can actually meet at all and the meeting is going to take place. So I'm going to talk about some recent advances in my group about the quantum chemistry of electronic resonances that are specifically designed for larger systems. And by that I mean specifically two developments: a resolution of the identity approximation and an integral screening scheme, both for complex scaled basis functions. And complex scaled basis functions are, as I will explain, an alternative to the absorbing potentials that Xenia presented yesterday. So in some sense, the whole methodology I'm going to present is complementary to what she talked about yesterday. So to get started, let's talk about electronic resonances briefly in general. So those are states that are unstable with respect to loss of electrons. So it can, for example, happen that you have a target that has a negative electron affinity, and then if you hit it with an electron, it doesn't form an actual anion, but it's also necessarily going to happen that the electron is scattered off elastically. Instead, it can linger around for a while, typically femtoseconds or picoseconds before it's released again, and that is what we call a temporary anion, and that's the type of electronic resonance. Or alternatively, it can also happen that you have that you perturb a system so strongly with an external force, typically a laser, that previously bound levels become unstable towards the loss of electrons. Those are called Stark resonances, and again, you have the situation that electrons can leave the system. So where it's relevant? Well, you need free electrons, you need lots of energies, so extreme environments come to mind, such as ionizing radiation, plasma, combustion, lasers, and that's of course all correct. I just want to add here that this is not only relevant for small systems like atoms and diatomics, but also to larger systems. In larger systems, it can happen that those processes become relevant. Think about, for example, the damage done to DNA by low energy electrons, or think about the machining of carbon materials using lasers. In any case, you create a is something going on? Seems to be a technical glitch, right? Anyhow, so in any case,
the problem is that slides are not changing. We only see the first slide.
Okay, well, that's weird. So
so try to change it, or then unshare and share again.
Well,
unshare.
Do you see now another slide?
Page, yes.
Okay, so
thank you.
Yeah, so we're talking about electronic resonances, right? And I was going to say that you have two types, which are either order ionizing, or so those would be temporary anions. You hit a target with an electron, it is not scattered off elastically, but apply an external force, and the electron previously bound levels become unstable with respect to loss of electrons. Those are called Stark resonances, and those are created by external laser fields. So it's relevant when you deal with high energy environments such as ionizing radiation, plasma, combustion, lasers. They all come to mind. And as I already alluded to, they are also relevant if you deal with complex systems and larger molecules. You can think about, for example, the damage of DNA done through ionizing radiation, or also what I'm going to concentrate and talk today, for example, the machining of carbon materials using lasers. In any case, you create locally a plasma. Electrons have the capability to leave the system, and in that way, we have to care about those type of states. Now, in the talk today, I want to concentrate on the systems depicted here on the right. So the Stark resonances, which are formed by the interaction of molecules with strong laser fields. But of course, we need to establish what strong means. And in order to do that, let's look in some more detail into light-matter interaction in general. So if we, I'm a chemist by training, and in that sense, I'm used to think about this perturbative regime first, where the intensity of the external field is low compared to the intermolecular forces, and then you can treat the interaction of the system with the field in terms of perturbative quantities, polarizabilities, hyperpolarizabilities, and so forth. But today I want to talk about something else, that happens if you crank up the field strength. So this is what strong field physicists usually care about. But then there is also a regime that is accessible with modern lasers, where the intensities that we deal with are so high, certainly higher than atomic units, that the details of the molecular electronic structure are not relevant anymore. I want to talk today about a region in between. So where the intramolecular forces are of the same order of magnitude as the laser field you apply. And this is a regime where where something happens that I would call strong field chemistry. Processes like Coulomb explosion or high harmonic generation, for example. They are driven by something called quasistatic ionization. And in order to treat that, you can use a very simple Hamiltonian. The dipole approximation is still valid in this region, so we don't have any fancy terms. Also, relativistic effects are not yet relevant. We can use a very simple Hamiltonian. We just cannot invoke a perturbative treatment because the two terms in the Hamiltonian are of the same order of magnitude. So what's this quasi-static ionization? Well, it's what I had already in the introductory slide. You add simply this type of potential to a normal Coulomb potential, and you get such a situation where a previously bound level is now unstable because a tunneling process can happen and the electrons can all leave. However, we can invoke here a useful approximation, namely this quasi-static approximation, and that is we can very often assume that the ionization is fast compared to the frequency of the laser. So this is a snapshot, and after a certain time, this will flip around and it will look exactly reverted. Now the question is, on what time scale does that happen? Is the electron still busy getting out when the laser flips around, or has it already left? And in typical applications of high harmonic generation or Coulomb explosion, the electron has long departed, so we can invoke this quasi-static approximation and pretend that the electron would be exposed to a static field. Now, this is the Hamiltonian we want to look at. It looks very simple, but it doesn't have any bound states. Instead, the states which are bound without the field have been turned into Stark resonances. And if we now care to look at larger systems, molecules, questions like anisotropy, for example, become important, because you want to know, is it easier to ionize some molecule if you hit it with a laser perpendicular to the molecular structure, or maybe in this direction or the other one? It's not obvious what the ionization rates that you get from that will be. And that is due to the fact that different ionization channels contribute in a different way, depending on the orientation of the laser field. So different molecular orbitals are more or less prone to ionization depending on what the external laser looks like. Another question we need to deal with is electron correlation. So is it okay to invoke the Hartree-Fock approximation or not? And this formula, which goes back already to a work by Robert Oppenheimer in 1930, shows that it's probably not okay to do the Hartree-Fock approximation because you see the ionization potential goes in as the exponential into the ionization rate. In any case, we need an unbiased ab initio description, and that is what we set out to develop. What is the basic challenge? Well, the same as for all resonances, the wave function doesn't vanish asymptotically, but it's coupled to the continuum. In theoretical chemistry, we usually deal with this situation where the wave function is confined in space. So we need it has only a finite extension and falls off to zero. if it's coupled to the continuum, the problem is the energy spectrum is also continuous. The resonance, this red state here, is not a discrete solution, but it's embedded in the continuum and only an increase in the density of states. So the state that we want to describe, X, is actually embedded in the solutions of the cation and electrons, yeah, somewhat away or even further away. Those are the dotted lines in the plot here. Now, one way to solve this is to solve the Schrödinger equation with outgoing boundary conditions. So we look for solutions that asymptotically don't go to zero, but behave as a plane wave. And then if we solve the Schrödinger equation with this modified set of boundary conditions, the resonance becomes discreted from, separated from the continuum. It becomes a discrete state. And as a consequence, the energy, the eigenvalue that we get out is now complex. And this imaginary part of the energy is the ionization rate at which the electrons leave the system. Now, how do we impose outgoing boundary conditions? It doesn't look very appealing to actually implement this. And that is why techniques such as absorbing potentials or complex scaling have been devised. And I want to talk about, I want to concentrate today on the complex scaling. How does it work? Well, it's a regularization procedure of the Hamiltonian and its solutions where you scale all the coordinates. This is just in one dimension, but it works the same way in 3 dimensions with a complex number. And if you think about such a solution that I had on the previous slide, you can on one piece of paper work out that this is going to be regularized if you scale the coordinates like that. Now, what is important to understand about the complex scaling is it's only the asymptotic behavior of the wave function that matters. You can add whatever locally confined potential you want here. It's not going to change the way it works. Doesn't matter how your molecular potential looks like because it vanishes at infinity. And what you need to regularize is only the kinetic energy in the case of order ionization. Now, quasi-static ionization is different because here we have a static field which does not vanish at infinity. And this is why the original theory of complex scaling devised by Balzlev-Combs foremost is not applicable because you have a different asymptotic behavior. So how is it relevant? Well, in some sense, you can say the regularization works as well. This sort of wave function is also regularized by complex scaling, but you see the difference if you look at the spectrum of the complex scaled Hamiltonian, because in the case of order ionization, you have so-called rotated continua. This is the theory that you find in the textbooks about complex scaling, but it's not applicable to the quasi-static ionization. In quasi-static ionization, you don't have any rotated continua because you don't have any bound states anymore. You don't have any thresholds. You just have some discrete solutions, which are those Stark resonances. And that is mathematically mostly being worked out by Ivar Herbst already 30 or 40 years ago, but it's largely overlooked, I think, by the chemistry and physics community. Now, we want to deal with molecules. So how do we combine this theory of complex scaling with a molecular Hamiltonian? Well, the problem is if we want to apply the Born-Oppenheimer approximation, it's not going to work, because if you think about this, we have, and start from this Hamiltonian and want to invoke Born-Oppenheimer, we have 2 ways to do it. We can either do complex scaling first, scale everything, and then do the Born-Oppenheimer approximation. That leads to complex nuclear positions. Nobody knows what that means. There are ideas how to remedy the situation. Something called back rotation has been proposed by Moiseier, for example, but it's involved. The other way would be to do the Born-Oppenheimer approximation first, so clamped nuclei approximation, Tn equals 0, and then scale only the rest, only the electronic coordinates. That leads to this sort of electronuclei interaction, which has also a problem because it's not an analytical function. That's a very abstract term, but you can see the problem physically if you think about the cusp condition. This is not going to be singular at a single point as without the scaling. Instead, you have a whole sphere, so the physical description is really messed up. So this doesn't work, and we need something else. Fortunately enough, there is something else, and that's called exterior scaling. So we don't scale the region of the space in white here, where you have the interaction of electrons and nuclei different from zero, but we only scale this outer region, which is in gray here. And in that way, we avoid the problems with the non-analyticity of the electronuclear interaction. However, if you really want to evaluate matrix elements over this operator, it's going to be very involved, because all the formulas that have all this machinery that has been devised over the last couple of decades is not going to be applicable, because you have to do integration in parts, so to say, in different regions of space. So it requires some further rearranging, and that is done by realizing that you don't necessarily have to scale the Hamiltonian itself. This is equivalent to not scaling the Hamiltonian, but the basis in which it is represented. So from here to here, we have just done a single coordinate transformation. So here we scale the basis in which the Hamiltonian is represented instead of the Hamiltonian itself. And that can then be further rearranged. These basis functions which have a scaled coordinate can be further rearranged to basis functions with a scaled exponent. And that is then a method that is easily implemented, because you just have to teach your quantum chemistry software how to handle complex valued exponents. And if you then combine it with the idea of exterior scaling, you get a method that is applicable to molecules within the Born-Oppenheimer approximation. And you do that by only scaling the diffuse functions. So only the functions that have a non-zero amplitude, so to say, in this gray region here, are going to be scaled. The steep functions in the middle that describe the core region are left unchanged. So this is what we want to combine with the established electronic structure methods. But before we do so, I maybe want to establish briefly how accurate this actually is. And so for small systems, for example, a helium atom, we can do a full dimensional solution of the time-dependent Schrödinger equation. So propagation in time without any complex scaling, and compare the ionization rates from such a treatment to our non-Hermitian time-independent treatment. And this is what we do here for different field strengths. So this is the ionization of helium at different field strengths, and what is plotted on the y-axis is the ratio between the non-Hermitian time-independent and the time-dependent ionization rate. So ideally, it should always be 1, but you see the deviation is about 5% at most at all field strengths, except at very low field strengths, and here it deviates. So why is that? Because the ionization rate itself becomes low, and that is very easy to understand, because in order to describe the ionization procedure, you need to describe all this region that the electron has to tunnel through. And if the external field F becomes lower, this region is of course more extended, because the distortion of the potential is less. So you need more and more functions. You need to, because this point where the electrons comes out is further and further away. And this is simply what you see here, that it becomes unreliable if the field strength is low. But other than that, it works very well. And it works also, I should point out, a lot better than for autoionizing resonances. This latter fact is, in my opinion, due to this correction that we devised. So it's possible to take out, so to say, the effect of the complex scaling due to the finite basis set representation by correcting the energy like this. So you see here that we subtract something which is the change of the energy at the field strength 0. And if we do that, the results are much better than with other types of resonances where this is not possible. Still, we have to determine an optimal scaling angle. We do this by minimizing the derivative of the energy with respect to theta. It's akin to what Xenia talked about yesterday in terms of caps, eta trajectories. In any case, it increases the computational cost, and because you need typically like 10 to 15 of these calculations. And I should also turn your attention to the basis that is used here. So it's very large. If you use a smaller basis, you won't see anything. So those are the two things that drive the computational cost. You need multiple calculations and large basis sets. Now, how can we do this now for extend or apply this to extended molecules? Well, one thing we came up with is an integral screening scheme. And the problem here is the following. Usually in Hermitian quantum chemistry, you can apply the Schwarz inequality. So for every 2-electron integral mu nu sigma lambda, you can get an estimate, a strict upper bound, by looking at the diagonal elements of the electron repulsion integral tensor. But that's not applicable here, because our electron repulsion integrals are not positive semi-definite. So we need to do something else, and what we came up with is a non-Hermitian generalization, which involves those additional integrals which have a complex conjugated exponent in the bra here. And this then works similar to the usual integral screening scheme from Hermitian quantum mechanics. And here we looked at the screening efficiency for a dimer of 2 benzene molecules with different monomer distances. Well, it's no surprise that the screening efficiency gets better if the dimer is torn apart, because of course that's what you always see independent of any complex scaling. The overlap of the functions is worse, and so you need less matrix element to consider. But what is interesting here is this plot on the right, where we looked at the screening efficiency for different integral classes. And by integral classes, I mean how many of the functions in here are complex scaled. So we have a class where nothing is complex scaled, and that is where the screening works best. And then you see the more functions are scaled in the 2-electron 4-center integral, the worse the screening efficiency gets. And also you see with the screening, with the scaling angle, the efficiency also goes down, but still it helps a lot because you need to, especially in extended systems, compute far less integrals. Now, the other development that I want to introduce is a resolution of the identity approximation. That is also well established for more than 40 years in quantum chemistry. You approximate the electron repulsion integrals in terms of 3 center quantities using an auxiliary basis set. Those are typically also Gaussians. And then you determine the fitting coefficients, which are these, by minimizing the deviation by the original generalized densities created by the original pair functions here, and the approximate densities created by the spanned by the auxiliary basis set. Now, in our case, this is not applicable in a straightforward sense because you cannot minimize a complex number, and our densities are complex in non-Hermitian quantum chemistry. So what we did instead is minimizing a complex valued, minimizing the absolute value of the complex scale density, and then you can basically work it out as usual. In the first approach we devised a year ago, we chose everything complex, so also the basis functions, the auxiliary functions here are complex. And then you need to use a Takagi factorization, because this is not so easy to invert if you have a non-Hermitian matrix. But then in this year, we realized this is actually not necessary, and you can get absolutely acceptable results by using only real valued basis functions as auxiliary functions here. And we use just standard basis sets and they work fine. And I just want to point out a connection here to something the late Martin Schütz realized about RI approximation of gauge including atomic orbitals. because he realized if you want to approximate gauge including atomic orbitals with RI methods, you also don't need any B field, magnetic field dependence in the auxiliary functions, and this is just the same what we see here for the complex scaled methods. So this is now implemented for MP2 and Hartree-Fock in QChem 5.0, available for, yeah, it's included in the public version of this. And I just want to come back to those questions I raised in the beginning and show you how our method works. So how do we describe such systems, the anisotropy and electron correlation effects in particular? As I said, our approach is here this RI-MP2 scheme coupled with complex scale basis functions. And let's look first at a very simple example to establish the accuracy. So here we look at the nitrogen molecule and its ionization at a pretty low field strength as a function of the angle of the external field. So 0 is parallel to the molecular axis, 90 is perpendicular. And as you see, the MP2 methods very well reproduce the CCSD, and the canonical MP2 and the RI MP2 are actually almost indistinguishable. And you also see Hartree-Fock fails completely. You don't get any anisotropy with Hartree-Fock. What are the computation times like? Here we look at anthracene, 24 atoms, and 1 complex energy point. And as for other RI methods, the most you can save actually by looking at applying it to the Hartree-Fock part. So you see here, this is a logarithmic scale. You have gigantic savings, 2 order of magnitudes when you go from canonical Hartree-Fock to RI Hartree-Fock. And what is important to realize here is, of course, you don't want only 1 complex energy because you have multiple orientations. And for every orientation, you need to re-optimize the scaling angle. So this comprises in total maybe 40 to maybe 50 complex energy calculations. But if one is just less than 10,000 seconds, so just 3 hours, you can easily complete this. And you also see if you have a purely real basis set, you can save some more, and it really gets a routine task almost. Now, some application to a number of acenes. So we go here from anthracene to tetracene and pentacene and look at the ionization rates as a function of this extension. So the field strength is always the same, and the laser is always in this XZ plane. So 90 would be perpendicular to the molecule. And you see it's always hardest to ionize if you hit it perpendicular to this molecular plane. But you also see how it changes if the molecule becomes more extended. See the ionization rate goes always up. And you also see the impact of correlation has a tendency to go down a bit. Well, we're not yet here, but we can now actually think about questions like how would graphene or nanotubes or fullerenes or these materials behave in laser fields? Because,
sorry, 1 minute remaining.
Yeah, I have 2 slides. So we now have a method that we can apply to those extended types of systems. So, and with that, I want to sum it up with some general conclusions. So I believe the chemistry of electronic resonance is exciting. We have new chemistry. It's a challenge for theory. We treat it in terms of complex valued energy. And now we have some tools devised for larger systems, such as an integral screening scheme and an RI approximation. Our RI MP2 method is very well suited for systems up to 50 atoms at the moment. There are easy ways to extend it further. It's suitable for quasi-static ionization. And we also have some work in progress on corresponding methods for order ionization, namely RICC2. And we also work towards microsolvation effects in terms of embedding. With that, I want to thank my group first, and especially Dr. Hernandez Vera, who did most of the work that I presented today. He implemented all this RI MP2 method I also thank the other people, my collaborators, of course, and the funding agencies. Thank you very much.
Thank you. And there is a question from Ugo. Theoretically, one can fix the laser orientation with respect to the molecule, but experimentally?
That is possible because you can do a pump probe experiment where you, so to say, have an orientation pulse first, which is weak but aligns the molecules, and then you have a stronger pulse which actually causes the ionization.
Can I ask a further question?
Yes.
Yeah, it's true what you say, and that's the answer I expected, but it's not so easy experimentally, and usually one has to average over different molecular orientations. So what happens in your calculations if you average? I mean, that means calculating a lot, but have you tried?
We haven't, well, we have tried, but we don't have any, so to say, numbers that are ready to present. But for the molecules I presented, so these Acenes, for example, we pretty much have the whole three-dimensional space. So it would be an easy task to perform this averaging.
Okay, thank you very much.
I have one short question. How do you generalize the variational minimization in Hartree-Fock for the complex energy?
So we have a, so to say, stationarity principle. So it's not a minimization, but a stationarity principle in our case.
Okay, so let's thank the speaker again.